Hello and welcome back to the discussion on greedy algorithms. In the previous video, we have seen several greedy algorithms for this problem. Most of them don't work, and when it works, the harder part in greedy algorithms is to prove why greedy algorithms are correct. In this video, we'll define an abstract notion called Metroids. We'll define what are Metroids, then we'll define a Metroid problem on the weighted Metroids. Then we'll give a greedy algorithm to solve the Metroid problem, and we'll formally prove that this greedy algorithm that we defined will give us the optimum. So this this Metroids gives us a framework to prove the correctness of the several greedy algorithms. In the next video, we'll take a concrete example. Then we will show how to map it to the Metroids. And once you define that, so the problem, the mapping that is in fact is a Metroid, then the greedy algorithm and Metroid will give us straight away the algorithm. And also, since the greedy algorithm on the Metroids is optimum, so whatever the greedy algorithm that we defined on the problem that we started with, which we converted into, which we show that it's a Metroid, the greedy algorithm will be optimum on the problems that we are going to show. We'll see some more such examples in the next class. In this video, we'll start with the definition of Metroid, and so what is the problem that you're going to solve on the Metroid, and what is the algorithm, and why the algorithm that we consider on the Metroid is in fact is the optimum. Continuing our discussion on greedy algorithms, today we will study what are known as Metroids. Metroids characterize a group of problems for which the greedy algorithms yield an optimum solution. We first define what's a Metroid, then we define a Metroid problem on the Metroid, then we give a greedy algorithm to solve this Metroid problem, then we show that the greedy algorithm that we define to solve the Metroid problem is in fact optimum. Let's get started with the definition of a Metroid. So in the Metroid, we have a base set which is called as S. We can assume that it has n number of elements, which is finite set. Now you take any collection of subsets of this set S. Okay, we will call the subsets of S which you are considering as independent sets in all our discussions. This collection of subsets of S, we will call it as F. This F along with the set S. Right, so S comma F. S is the base set and F is a collection of subsets of S. This collection of subsets is said to be, this pair is said to be a Metroid if and only if the following three conditions are true. The zeroth condition is that the empty set should be independent. In other words, empty set should be part of F. If B is in the collection, so that means that if B is an independent set, then if you take A which is a subset of B, then A also should be there in F. In other words, if you take any set which is independent, every subset of an independent set should be independent. Here B is independent. If you take a set A which is a subset of B, then B has to be there in the collection. And the third property is also important. If A and B are two independent sets, that means that A and B are part of F, and the cardinality of A is smaller than the cardinality of B, then there must be an element in B which is not there in A, such that the A union X should be in F. In other words, if you take two different sets with different cardinalities, with both of them being independent, then there has to be an element in the bigger set which is not part of the smaller set, such that when you add this element that you considered to the smaller set, then the X union, that should be an independent set. You should be able to find an element in the bigger set when you which is not part of the smaller set, so that when you add it to the smaller set, the set actually becomes independent. If these three conditions are satisfied, then the pair S comma F is said to be in Metroid. Now let's define what is a Metroid problem. We can define what's a weighted Metroid. Weighted Metroid is nothing but we associated with every element in the set S with a real valued number. right? So this every element in a set will be given a weight, right? So there is a weight function which assigns a real valued number to every element in the set S. Given a subset of a set S, now we can define the weight of the set. The weight of the set, as you look at every element in the set and add up the elements of each of these individual elements. So the weight of a set is defined as the sum of the weights of the individual elements which are part of the set. Now the problem is to find a independent set with the maximum weight. So you have given a collection, you have given a base set, you have given some weights associated with each of these elements. Once you are given the weights associated with each of these elements, we can define weight as a subset. Weight of a subset is defined as the weight of the individual elements in the sets. Now among all the independent sets, we want to find a set whose weight is maximum. So let's say that n is the number of elements in the base set and m is the number of elements in the f set. If the one of the brute force way of doing this is just look at the every subset in F, right? So given every subset of F, the weight of the set can be computed by adding the weights of individual elements that can be done in order n, right? So you can explicitly go and look at each of these sets, compute the weight of each of these independent sets. In order to compute the weight of an independent set, it will take order n time. So if you go through each of the sets and find the weights and keep track of the maximum weighted it will take order n into m time. But you notice that f is a subset of power set of s. So m can be as big as 2 to the power n. So the order n into m is an exponential time algorithm in n. So we need something which only depends on n, not on m. Right, so as of now this m can be exponential, so this would imply that so this algorithm is exponential. So we are looking for an algorithm which is polynomial in the size of the base set. Okay, so if f is independent, then you can ask me, so how will you give me the set f, which is the exponential number of subsets of s. In general, what is given is that this family of independent sets is not given to you explicitly. So what is given to you is a function, right? So it's in, let's call this function as is independent. It will take a subset a of s, and this will return this is a boolean function. This will return true or false. If a is independent, when you call this function is independent of a, it will return true. If the function, if a is not independent, that will return false. So what you have is an access to such an set, such a function. Given a set S, it will tell you whether it's independent or not, right? So if you want to explicitly go and look at what are all the elements which are there in F, then you have to make 2 to the power n calls to this, and so that will take exponential time, right? So we will not have access to every independent set, but given a set, we can always figure out whether this is an independent set or not. And this is independent set, let's call this as an f function. The complexity of answering this need not be order 1. In general, let's say that it takes f of n time to answer whether a given set is independent or not. So we are looking for an algorithm which will find the maximum independent set, and we are looking for an algorithm which only depends on the number of elements in the base set, but and also you are given a function which will tell you whether given a subset of yes, whether this will be independent or not. So with that, let's look at the greedy algorithm. So what this greedy algorithm does is that what is given to you is the base set S, and there is an independent function. Then there is an f. This elements in f can be obtained by querying. Given a subset of a, you'll have a function which will tell you whether it is independent or not. Then there is a weight function which is associated. Every element in S will be given in S. So A is this set which is eventually you are going to return. Since A is equal to empty set, which is going to be an independent set. Since we are looking for an element with maximum independent weight, So what we will do is that you sort the elements in the decreasing order by their weights. Now you consider each S in the monotonically decreasing order and ask the question whether A union F will be in F. This is answered by our function. If you A is independent, now you want to know whether A union X, can you add X to A but still the new set after adding X into A will continue to be independent. This can be checked by calling the is independent function. For the is independent function, U is called with parameter A union X. If this happens to be an independent set, then we will update our A to be A union X. If A union X is not independent, that means that A union X is not in F, then we will discard this X and consider the next element. So at the end of this algorithm, so whatever is our A, at every point in time when you update an A will always be independent. X will be considered in the we will consider the elements in the decreasing order of the weights, and we will add it to the independent set only if after adding this X into the independent set the new resulting set is still going to be independent. Only then we will add this X into the set that we are maintaining, which is A. So at any point of time this A will be an independent set. At the end of the algorithm we will return this A. So this is a greedy algorithm because since we are looking at the maximum independent set, we will consider the maximum weighted edge first, maximum weighted element first, and then consider the rest of the elements in the decreasing order of their weights. So before coming into the proof why this is correct, let's quickly analyze what is the time complexity of this. We need to sort the given set of numbers in the decreasing order of the weights. If S has n number of elements, then this will take n log n time. So then we consider each of these elements in the decreasing order of the weights and then check whether A union X is independent or not. So every element will be considered exactly once. So the loop will run n number of times, and each time when you consider, we will call the is independent function, which will take the parameter as A union X, and if A union X is independent, then we will update our A to be A union X. Okay, so if A union X is not independent, then we will not update our A will continue to be there. So every time when you consider a number, we need to ask whether A union X is independent. So this function is called n number of times, and our assumption is that if this is independent function will take time f of n, right? So in order to given a set S, in order to decide whether this is part of the set is in S, is in F, this will take f of n time. So depending on the algorithm, so depending on exactly what is that and how quickly we can decide that a set is independent, in other words a set is in the family of subsets that are given to me, the complexity of the algorithm will depend on the f of n, which is the complexity of the function to decide whether a set is independent or not. So you first sort the sequence of elements, that will take n log n plus n into the complexity to check whether an element is independent or not. Now let's pay our attention to why this algorithm is optimum. We need to show that in fact the set K that we get at the end of this greedy algorithm is in fact will be an independent set with the maximum weight. For contradiction, let's say that the algorithm, the set A that it returns is not the maximum. We will call the set A, which is the greedy algorithm returns, as G. Okay, G is the solution given by the greedy algorithm. For contradiction, we will assume that G is not optimum. If G is not optimum, then there exists a independent set with a bigger weight. Let's call that as optimum, OPT. So this optimum has a weight which is bigger than the weight of the greedy algorithm. Okay, let's assume that the optimum picks O1, O2, O of A, and G is another set of elements. Both the sets are independent sets, and let's say that this has b number of elements. First we show that the A has to be B. So the number of elements in both greedy and optimum are same. Without loss of generality, we will also assume that weight of each of them is positive, because if the optimum has a element whose weight is negative, then you can ignore that number. So whatever element that you have, since if you delete an element, what you get is a subset of an independent set, which is since it's a Metroid, property is satisfied, so the new set is also going to be independent. That will have a weight which is smaller than what you started with. So we will assume that the optimum will not have negative weighted elements. Similarly, if the greedy had negative, if the original set has weights with negative weights, then our algorithm will stop when we start seeing negative elements. That means that our greedy algorithm will never pick any negative elements. So we will assume, without loss of generality, we will assume that both of them have weights of all the elements in G as well as optimum are all positive. Now if A is greater than B, so that means that the number of elements in optimum is greater than the number of elements in G, then by the exchange property, there has to be an element in the optimum which is not in G. When you add it to G, the set should become independent, right? But the greedy algorithm should have considered such an element, and it did not pick in G because when you try to add it to G, it was not independent. So such a thing cannot happen. And similarly, if the cardinality of G is bigger than the cardinality of the optimum, then again by the exchange property, there has to be an element in G which you can add it to the optimum, and after adding to the optimum, the set still continues to be the independent because of the exchange property. If that happens, since we are adding an element with the positive weight of the set after adding it to the optimum is also independent, so the weight of that actually increases. That is a contradiction to the fact that what we have is an optimum independent set. So these two arguments implies that the number of elements in optimum as well as in greedy or both of them are same. So we will assume that both of them have k number of elements. So the elements in optimum we will denote it by O1, O2, OK, and the elements in G we will call it as G1, G2, G3, G of k. We will also assume that these elements are sorted in the decreasing order, and the elements in G are also sorted in the decreasing order of the weights. In other words, weight of O of I will be greater than weight of O of I plus 1 for every I. Similarly, weight of G of I will be greater than or equal to weight of Ji plus 1. Now we will do a pairwise comparison. We will check how does the weight of O of 1 compares with the weight of G of 1. We will compare how does weight of O of 2 will compare with G of 2. How does weight of O of 3 compares with G of 3, and so on. If weight of G of I is all greater than or equal to weight of O of I, right? When I do the pairwise comparison, if for every element in G, if the total weight is greater than or equal to weight of the optimum, then if you just add the summation on both sides, you will get that weight of G is greater than or equal to weight of the optimum. But what we for a contradiction, we have assumed that the weight of the optimum is greater than the weight of the greedy algorithm. So there has to be an I such that when I do the pairwise comparison, weight of O of I is greater than weight of G of I. If weight of G of I is smaller than or equal to weight of O of I for every I, then you add up on both sides, what you get is that weight of G is greater than or equal to weight of optimum. Right? Since that is not the case, there has to, when you do the pairwise comparison, there should be one pair such that where the weight of the solution element in the optimum is greater than the weight of the solution in the greedy algorithm. So among all such pairs, we will pick the one which has the smallest, right? So we will pick an I such that it's the smallest I such that weight of the optimum is greater than weight of the G of I. Now so let's consider this set now, right? So these two subsets, optimum dash and let's call it as G dash. This is a subset of the optimum, right? So this is a subset of the optimum, and the other side that I have here is a subset of G, right? So in the first element, in the optimum dash, then there is IL number of elements, and in G dash what I have is that I have I minus 1 set of elements. Since optimum dash is a subset of optimum, optimum dash is an independent set. Similarly, G dash, which is a subset of G, is also an independent set. Since both of them are independent sets, and you notice that the optimum has I number of elements and the G dash has I minus 1 number of elements. So the cardinality of optimum dash is greater than the cardinality of G dash. So there has to be an element in the optimum dash which is not in G dash, such that when I add it to G dash union O of J, right, so we will call it as J here. That element is O of J. We have written J is smaller than I, smaller than or equal to I, right? So smaller than or equal to I, such that O of J union G dash is independent, right? So this is by the exchange property, because the number of elements in the optimum dash is greater than the number of elements in G dash. So there has to be one element in the optimum dash which is not there in the G dash, but G dash union optimum dash has to be independent. So we will pick such an O of J. This O of J weight will be greater than or equal to weight of O of I, right? So it is picked from O of J is one of the elements in O of I. Since the sequence is in the decreasing order, the O of J will certainly have a weight greater than or equal to weight of O of I. If it is O of I, then it will have the same weight, but if it is not O of I, then it will certainly have a weight which is greater than or equal to O of I, because this has to be one of the elements on the left hand side and the sequence is decreasing. But notice that O of I, weight of O of I is greater than weight of G of I, right? So O of I is not in G dash, but the weight of that is greater than weight of G of I, right? So the O of J should have been considered before the greedy considered G of I, and we are saying that this proof says that O of J union G dash is an independent set. So the greedy should have picked O of J instead of G of I. So G of I, O of J should be considered before we consider G of I, and since O of J union G dash is independent, the greedy algorithm should have picked O of J before it picked G of I. So this is a contradiction. So if contradiction is the fact that the greedy algorithm has not picked O of J, right? So this O of J, existence of O of J comes from the exchange property, and the second property is also important because the sets that I considered here, which are all subsets of the optimum and the G, these subsets that I considered are independent because of the first property, the property number 1, which says that independent set, subset of an independent set is an independent set. So these two properties, both the hereditary property and the subset property, both are important in proving that the greedy algorithm that we considered for the Metroids are optimum. So the contradiction has happened here with G dash union O of J should have been independent. If this was independent, then the greedy should have picked it, right? So, but greedy did not pick it, so that's a contradiction. The entire contradiction has happened because we assume that there is a set optimum whose weight is greater than the weight of the greedy solution. So the algorithm, the set which is written by the greedy algorithm is in fact is the maximum independent set. Suppose if you want to find a minimum independent set instead of maximum, then what all you need to do is to, instead of considering the elements in the decreasing order of the weight, so you can consider the elements in the increasing order of the weights, and you can rewrite the entire proof that I showed you. Instead of greater than or equal to symbol, you can flip it with the smaller than symbol and rewrite the entire proof. Other way to argue is that you can just multiply all the weights by -1. So now instead of maximizing, you will end up minimizing, right? So the same proof actually works, right? So before multiplying with -1, if you had found the maximum independent set, and if you after you multiply -1 and if you consider this and find the maximum independent set, you will be actually finding the minimum independent set in the before multiplying. So this is only for the sake of the proof. You can either rewrite the previous proof, or you can convince yourself by multiplying with -1 and say that after you multiply -1, if you actually find the maximum one, it's actually before multiplying, it's the minimum independent set. So if you want to find, the model of the story is that if you want to find the maximum independent set, you actually sort the sequence in the decreasing order, and if you want the minimum independent set, you consider the elements in the increasing order of their weights. So one of the quick example is that you are given a matrix n cross m matrix, and each column has a weight associated with it, and you want to find a subset of columns which are all independent with the maximum weight. So when do you say that a subset of columns are independent? If it is a subset of columns is said to be dependent if you can write them as a linear combination of them can be written as 0, right? So if one of them can be written as a linear combination of the other ones, then the set of columns that are given to you will be dependent, right? So if it is independent, means that these you cannot find with the linear coefficients. When you add this up, you will get a 0. Okay, so if you want to find a subset of columns which are all independent with the maximum weight, so what you can actually show is from the linear algebra that this is a Metroid. So where the given set of columns are your base set S, and if you take any subset of these columns, that is your the set F. So what we can show is that this in fact forms the Metroid. So once you know that this is a Metroid, then what you do is that you pick the column with the maximum weight, and then you consider the columns in the decreasing order of the weights, and when you try to add something into the one column into the existing independent sets, you have to just check whether the newly considered column, when you add it to the existing collection of columns, whether the entire set becomes actually independent. You know that this can be looked at by looking at the rank of this collection of columns. Okay, so in order to decide whether when I add a column to the existing set of columns, whether the whole set is going to be independent, is actually answered by looking at the rank of these the submatrix that you're going to consider. So you're going to repeat this n number of times, and you will get an element whose you can find an element who you can find a collection of subsets, collection of columns which are independent and has the maximum weight. In this video we have seen so what are Metroids, and what is the algorithm, greedy algorithm that is used to solve the Metroid problem. And we have seen one concrete example in the linear algebra which falls under the category of Metroids, and we have a efficient greedy algorithm to solve the problem. In the next videos we'll see more examples which can be mapped or related to the Metroids.